Okay, good day everyone. So in this video, what I want to do is I want to talk about functions in R. And you can really think of a function in R as being the same thing as a function in mathematics. So in mathematics, a function is just a way of relating an input to an output. And typically you see this notated in sort of the following way. Basically, you have kind of this fancy letter F, and you have some kind of input value, and that is equal to an output. So in plain English, kind of what this is saying is when you place something inside the parentheses here, you just get a corresponding output. So imagine you input $2 into a vending machine and you get a Coke as an output. In this case, we would say that the function of the vending machine is to output a Coke when you give it some money. So as an example of a function's use, that is to say, as a more kind of mathematical example of a function's use, we could create one that just outputs the square root of a number by writing something like f of x is equal to the square root of x. So in this case, x here is just acting as a placeholder, meaning that if we swap it out with a positive number, we'll get the square root of that number. So for example, if we insert the number 16 into our function here, like so, we get a value of 4. If we insert like a value of 25, we get a value of 5. So in this case, this kind of fancy letter F here just denotes the function's name, but you don't have to use this kind of naming scheme. This is really just a sort of formality that mathematicians have adopted. You can actually name or symbolize a function really any way you want. And to kind of see a nice example of this, we only need to really look at how R uses functions because they work identically to this. They're just named different things. So for instance, R has a function for finding the square root of a number, except that instead of naming that function f of x, it names the function sqrt of x, which is obviously just a kind of an abbreviated form of square root. So let's do this. Let's head over to RStudio here. So if we type sqrt, right, and inside the parentheses we just insert 25 and we run this line of code, you can see we get a value of 5. And rather conveniently, R will store the output of a function as an object if you ask it to. So if we type something like x, and then we give it our assignment operator, then we say sqrt 25, like so, you can see that line of code was sent to the console, and now if we just run x by itself, we get a value of 5. Now, as you might expect, given its kind of lineage as a tool for data analysis, R has kind of many such functions, and we're going to go through some of the more, I guess, commonly used ones here. Now, these aren't functions you need to kind of go out of your way to memorize, but they are sort of illustrative of how R works generally, and it's kind of good to know basic stuff like this exists, so you can always look it up quite easily after the fact. Now, one very common function is actually one we've already learned about technically, and it's called the combine function, or some people call it the concatenate function. So this just combines values into a vector. But you can actually also use this function for lists as well, which is something we'll discuss at a later point. So for instance, if we type x and we use our assignment operator, we type a little c and some parentheses, we can now include values that we want in our vector. So just say 1, 2, 3, 4, 5, like so. And we run x by itself, you can see we get 1, 2, 3, 4, 5. So it combined all of these values into a single object. Now, another very common function is the sum function. So sum, like sum. So if you have a numeric vector, like we do here with x, you can just take the sum of all of the values in x. So we just dump x into the function there, you can see we get a value of 15 because 1 plus 2 plus 3 plus 4 plus 5 is, of course, 15. There's also a function called CumSum, so C-U-M-S-U-M. And what this does is it takes the cumulative sum of all of the values. So if you dump in an x there and you run that, you can hopefully see what the function is doing. It's just kind of producing a rolling sum. So for instance, 1 plus 2 is of course 3, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10, and obviously 1 plus 2 plus 3 plus 4 plus 5 is 15, as we determined earlier there. There's also a function that counts the number of elements in a vector. So obviously, in a case like this with x here, we know that our vector contains 5 elements, but sometimes you're working with vectors that have hundreds or even like thousands of values, and you need to know exactly how many values it contains. Well, this is where the length function really comes in handy, because it will just quite simply count the number of elements for you. So if we just insert x here, you can see it spits out a value of 5. So if we wanted, what we could do now is we could kind of like easily calculate the mean of x here by just using the sum and the length functions that we've just learned about. So we could type something like the sum of x, and then we could divide that by the length of x. And that gives us the mean of x. Alternatively, R does have a function for computing the mean, and it's just quite literally mean. So if you run that, you can see we get the same value. There's also a function for computing the median. So it even has functions for the sample standard deviation and sample variance. So we could just type SD, insert x, and that gives us the sample standard deviation. We could also type var, insert x there, and that gives us the sample variance. And don't worry if you don't know what standard deviation and variance are at this point. It's just, I think, useful to know that these functions exist. Now, thus far, we've been kind of using these functions in a really simplistic manner. You know, we input something and then they give us kind of a simple numerical output. But the behavior of many functions is not actually a fixed thing. So most functions can actually be modified through the use of what are called arguments. So an argument, let's get some space here. An argument is simply a parameter, or if you prefer, like it's like a setting that allows you that allows you to customize how a function operates. So a simple example of this is the round function. So the round function is used to round numbers to a specified decimal place. So for instance, suppose we have a vector that contains both the number pi and the square root of 2. So we'll create a vector, and we'll just use x again. And inside our vector, we will insert pi, and recall r has a numeric constant for pi, and we'll say square root of 2, like so. So running that, you can see we now have a vector of 2 values, and both of these values have some nasty decimals in them. So what we could do is we can use the round function and its digits argument to round these values to a certain amount of digits. So for instance, like 2 digits. So we could type like round x and then put a comma and say digits and then set that equal to 2. And if you run that, you can see it rounds both of those values to 2 digits. Alternatively, you could round them to 3 digits or 4 digits. Or if you want to just round to the nearest integer, you can just set this to 0 and it'll round to the nearest integer. Now in the case of the round function here, it's only taking a single argument, but some functions actually have multiple arguments. So a good example of this is the sequence function, which just is used to generate regular number sequences. So for instance, suppose you wanted to generate a sequence of values from 0 to 100 counting by fives. To do this, there are 3 arguments that you're going to need to set. Let's actually write them out here. You're going to need to set the from argument, you're going to need to set the to argument, and you're going to need to set the by argument. So in the case of the example here, we're going to set from to 0, we're going to set to 100, and we're going to set by to 5. And when we run this, you can see we get a sequence of values from 0 to 100, just incrementing by values of 5. The sequence function here is also kind of illustrative of another feature of functions, and that's that they often have mutually exclusive arguments that you can appeal to. So for instance, instead of using this by argument, what we could have done instead is we could have used the length.out argument. And what this argument does is it specifies how many values we want in our sequence. So for instance, if we want to go from 0 to 100 and only have 5 values, we would type something like this. So if we run this, you can see we get a sequence of 0 to 100, and that sequence only contains 5 values. Now, to save yourself some time and effort when typing out functions and their arguments, you can actually just provide the values without the argument name. So for instance, we could have typed the sequence function like this. We could have said 0, 100, 5. If you run that, what you can see is we get a sequence from 0 to 100. And in this case, instead of producing a sequence of 5 values, it's actually counting by 5s, indicating that what we've typed here is actually using this by argument. It's not using the length out argument. But you're probably, the reason it's not using the length out argument is because in the ordering of the function's arguments, by comes before length.out. So it just defaults to using by. But you're probably wondering, how could anyone be expected to know that? Well, they basically would have looked at the help documentation for this function specifically. So every function in R will have associated help documentation. And for kind of novices with R, this documentation can sometimes be a bit intimidating. But as you get more proficient with R, it'll become a lot more straightforward. So to access the documentation, all you need to do is type a question mark followed by the name of the function. So if we want to look at the documentation for the sequence function, we just type question mark seq and run that. And RStudio will quite conveniently pop up a nice little window here that we can expand. So, looking at this, what you can see is the documentation here right at the outset gives us kind of a nice, somewhat technical description of what the function does right here near the top. And, it tells us there's a couple of other sort of associated functions that can be used for sequence generation as well. Next, what we can see is the document shows us how the function should be used. And this is actually where we can see what types of arguments the function has. And we can also see the order that they go in. So if you look here from kind of left to right, we have the from argument, we have the to argument, and then we have the by argument, and then finally we have the length.out argument. And interestingly, this by argument has this kind of nifty equation inside of it. And what this is sort of showing us is that when you specify the length out argument, the function is actually just using the by argument with this equation in place. And so maybe let's do this. Let's see if we can replicate, let's see if we can replicate our earlier result we got using the length out function with the by argument. So what we'll do is we'll type seq here. say 0 to 100, and then we'll say vi, and then we'll kind of make use of this little equation here. So basically the equation is saying parentheses, parentheses, so we want 0, actually no, we want 100 minus 0, right? And then we're going to divide that by 5 minus 1. So 5 minus 1, like so. So if we run this, we should get just 5 values. Running that, and look at that. You can see that's precisely what we get. 0 to 100, and there's only 5 values there. So it seems like this little equation worked quite well. Now just kind of quickly looking at the rest of the help documentation, you'll notice kind of some other nice features. So if we just kind of scroll down a little here, you can see we have a nice little written description of what each argument kind of does. And then there's some sort of additional details the programmers of the function kind of think it's worth knowing about. And then at the very bottom, if you scroll all the way down, you can see there's just some code examples that you can run. So all help documentation in R will pretty much follow this same basic layout. And I do encourage you to kind of look at the help documentation of some of the other functions that we've been using here, just to kind of get your foot in the door and get yourself used to looking at this stuff. Now, another interesting function. So another interesting function, let's maybe do this. What was I saying? Another interesting function that takes multiple arguments is the repeat function. So this function does pretty much what it says on the box. It just repeats stuff. So what we need to do is we need to tell it what it is we want to repeat. So for instance, if we want to repeat spam, we just tell it spam, and then we have to tell it how many times we want to repeat this. So we use the argument times, and we could say, let's repeat spam 10 times. And if you run that, you can see we get 10 spams. You can also repeat vectors as well. So if we type something like repeat, and we just say like 1 to 3, and then 10. What you can see is you get 1, 2, 3, 10 times. And if you want to repeat each item in the vector 10 times, followed by the next element, then what you can actually do is you can swap out the times argument for the each argument. So if we type, if we type repeat, right, and we say 1 to 3, and we say each, and we set that to 10, what you can see is we get 10 ones, 10 twos, and 10 threes. Another interesting function is what's called the sample function. So suppose you have a vector of values like 1 all the way to 666, like so. Actually, let's do this, just so we have kind of a nice clear console here. What we could do is we could use the sample function to take a random sample of, say, 13 values from this vector. And by default, this function will sample without replacement, but it does have an argument that allows you to sample with replacement if necessary. So what we could do is we could say sample x, and we could say size is equal to 13. And we can even store these values and take a look at them. So if we run this, what you can see is we now have 13 randomly selected values from this vector here. And if we wanted, we could put these values in order. So R has a function called the sort function. So we just say sort y. What you can see is it sorts the values from smallest to largest. In other words, it puts the values in ascending order. And of course, there is an argument that allows you to put them in descending order if you prefer. So that argument is decreasing, and you just simply set that true. So running that, you can see now we get the same values in descending order. So these are just some basic functions that tend to get used quite frequently. But of course, R has many other functions that we'll kind of see and learn about as we progress here. But before we leave, I think it's maybe worth pointing out that R does allow you to write your own functions if you decide to. Let's maybe just get some space here. And it has to be said, writing functions is as much an art form as it is a science. So for now, what I think we'll do is we'll just create a very simple function so that you can kind of get the gist of how this works in R. So let's do this. Let's create a function that simply evaluates whether a number is a prime number or not. And recall kind of from your basic education that a prime number is just a whole number that is divisible by 1 and itself only. So if you kind of think about what that means, any smaller whole number that you divide by, apart from 1 obviously, should always have a remainder. So remember remainders? So for instance, consider the number 6. If we divide 6 by 5, 4, 3, and 2, some of those divisions are going to have a remainder and some of them won't. And using R's modulo operator, we can actually look at the remainders of these various divisions. So for instance, if we say 6 and we type the modulo operator followed by 5, this is effectively saying 6 divided by 5, but it's only going to show us the remainder of this division. So if we run that, you can see we get a remainder of 1. If we do 6 modulo 4, run that, you can see we get a remainder of 2. If we do 6 modulo 3, we get a remainder of 0. If we do 6 modulo 2, we also get a remainder of 0. Now, if we contrast this with a prime number like 7, we're not going to see any zeros in our list of remainders, indicating that 7 is in fact a prime number. So if we type something like 7 modulo 6, you can see we get a remainder of 1. We say 7 modulo 5, we get a remainder of 2. Say 7 modulo 4, we get a remainder of 3. If you say 7 modulo 3, you get a remainder of 1. And then lastly, if you say 7 modulo 2, you get a remainder of 1. So what we could do is we could write a little line of code that kind of just exploits this characteristic of prime numbers. And it's a pretty simple line of code. We basically just say 7 modulo, and then we're going to give it a vector from 2 to 6. So we could say 2 to 6, like so. And if you run that, what you can see is we get the same remainders we got when we kind of computed them individually here. So except now we get all of the remainders as just kind of a nice convenient vector. So what we can do is we can ask whether all of these values are exactly equal to 0. And we can do that by just typing 2 equal signs and 0. Then if we run that, what you can see is we get just a bunch of logical statements, and in this case, every single one is false because all of these numbers are not equal to 0. And recall that in R, a logical false value is equivalent to a 0. So what we could do is we could actually take the sum of all of these values and we'll just get a value of 0. So if we say sum, like so, and you run that, you can see we get a value of 0. So the fact that the fact that this line of code outputs a 0 indicates that 7 is a prime number, because if we had used a non-prime number, we'd have at least one true value in this vector here, which means the sum that we're taking would have to be greater than 0. So as long as this little equation we've written here is exactly equal to 0, we know that we have a prime number. So that means we could actually extend this further and ask, is this equation exactly equal to 0? So if we put this kind of in parentheses here like this, we say exactly equal to 0 like so, we should get a true value. So we now have an equation that tells us whether 7 is a prime number. And in this case, it's saying that is true. So what we can do is we can actually generalize this so that it'll work with any number. So what we could do is we could say like x is equal to 7. Whoops. And, we could just copy this maybe, paste it in, and we could swap out the 7 here for an x. And where we have 2 to 6, we could just change the 6 here, basically just being x minus 1, like so. And now, if we run both these lines, we should get a true value. And you can see that's what we get. So now that we know how to determine if a number is prime, and actually we should actually check to see if this works with a non-prime number. So if we dump in a 6 and we rerun this, you can see 6 is false, indicating that it's not prime. If we type in something like 317, which is a prime number, and you run that, you can see it tells us that's true. So as I was saying, now that we know how to determine if a number is prime, we can take this and we can just put it inside a convenient function so that we don't have to repeat typing this entire line. So the way that process works is we first begin by just creating kind of a short name and specifying the arguments that our function will have. So in this case, our function is only going to have one argument, and that argument will be the number that we input. So we could call this function is underscore prime, like so. And then we would put an assignment operator, and we would type the function and input what we want our argument to be named here. So we'll just stick with the convention of using x. Then all we need to do is simply type our code inside the body of the function. And the body of the function is demarcated using curly brackets like this. So we basically now just type this. So let's copy that, paste that in, and we're done. So before we run this, it's maybe just worth pointing out the spacing that I'm using here. So I could have technically written this entire chunk of code on a single line, sort of like this. So I could have written something like this. But, as you can tell, that's kind of hard to read. Best practices dictate that for readability, the body of the function should really be on its own line, and it should be indented so that we know that it is part of a larger block of code. So let's maybe fix this so that it looks good. And you can see RStudio actually automatically indents for you, which is pretty convenient. So let's put this back to about there. And we can now run this. And once that's done and there's no errors, we can now use the function. So if we type something like is underscore prime, followed by some parentheses, we can now just insert a number and it'll tell us whether it's prime or not. So if we insert a 7 and we run that, you can see it says true, that is a prime number. If we insert a 6, it says false, that is not a prime number. If we insert what's a really big prime number, like 1997, right? True. If we change this to like 19995, maybe, you can see that is not a prime number. And of course, there's other things we could do with this function to improve it further. So for instance, as is, the function allows us to input, any number we want. But technically, you should only be allowed to input whole numbers greater than 1. And this is because prime numbers can only be whole numbers greater than 1. So, inputting pi into our function here should not give us anything resembling a sensible result. But you can see it tells us pi is a prime number, which doesn't make sense. And obviously, there's various ways you could have the function behave if someone inputs something that violates this rule. So, for instance, we could have the function throw a warning message, or we could have it throw an error message, or we could have it just evaluate to NaN, not a number. Alternatively, we could have the function take the user's input and just round it to the nearest integer and then, perform its usual calculation there. You could also set up the function so that it works with multiple values. So right now, if we input a vector of values, our function will just kind of produce a single answer. Our function will produce a single result like it's been doing here, but it'll also throw a warning message. So if we insert a vector like maybe 2, 3, and 4, and we run that, you can see we get a logical value here. But technically, we should have 3 logical values. We should have 1 for 2, 1 for 3, and 1 for 4. We shouldn't just have 1 in its entirety. And you'll notice we have also these warning messages that we should probably deal with. So that's another thing you'd want to probably fix with this function. It's also worth pointing out that the function we've created here is pretty shitty and inefficient. I'm sure there's math theorems that we could appeal to that evaluate prime numbers a lot more efficiently. But the thing is, adding in all of those features requires a bit more expertise with R than kind of the level that we're currently working at here. The point is not to create a flawless function. It's just to show kind of the basics of how a function is created.